Hello and welcome to this Seawind webcast about next level teetering. My name is Jeff Henderson and I'm a mechanical engineer from New Zealand with 40 years experience in the international wind industry, including founding a startup turbine manufacturer in New Zealand called Windflow Technology. Windflow built over 100 half megawatt two-bladed teetering wind turbines in New Zealand and Scotland, most of which are still running today, including a 46 megawatt wind farm on one of the windiest sites in New Zealand. Before I returned to New Zealand in the 1990s, I spent 7 years in California and England. In England, I worked at Wind Energy Group, WEG, and learned about teetering two-bladers when I became project engineer for the MS3 turbine. In 1989, I wrote a paper with WEG colleagues David Quarton and Roger Haines about teetering, and I'm pleased to say that they are online in this meeting today to talk about Seawind's innovative approach to teetering. I will introduce them later, along with our other two guests from England, former WEGies also, Andrew Garrad and Steve Gilkes. I'm currently based in Genoa, Italy, where I'm serving as Seawind's CTO. Seawind's founding CTO, Silvestro Caruso, is with me in person in Genoa. And we also have another founder, Martin Jakubowski, joining in a while, I think, and Deputy CTO Sesto Avolio, online from further south in Italy. This presentation is in 3 sections, and I will be stopping for questions after each section. So on with the presentation. Next level teetering. So I'll start talking about the history and fundamental advantages of teetering. Second section will be about the powerful force for stability, that is aerodynamic damping. And in the final section, I'll talk about scaling law issues. Section 1, Introduction to Teetering. So what is teetering? This slide ends up being a bit of a jumble of images, but the point of this, which Americans actually call a teeter-totter, the rest of us call a seesaw, is that teetering is as simple as the principle of a seesaw. And it's a question of balance. You have a natural equilibrium through having a hinge mechanism. It's a bit more complicated because the wind turbine is also spinning about another axis. And being an aerofoil, you get a powerful damping effect, almost as if the blades are trying to pass through a thick viscous fluid, which is what's symbolized here. And damping is very important because teetering is a resonant phenomenon. And so the amount of damping determines the teeter amplitude. There's even a second order differential equation, which I'll come to in the second section. So more simply visualized, teetering is this motion of the blades and hub on a hinge relative to the main shaft axis. And what does it do? This time series graph illustrates the great advantage of teetering, which is that it equalizes the blade root moments and out of plane moments on each blade. This graph actually shows 2 blades, blade 2 in red and blade 1 in blue. And the reason you can hardly see the blue is that it's overlain almost exactly by the other time series. The difference between the two is shown on the black line at the bottom, and actually the sinusoidal ripple that you can see there, the remaining difference between the 2 blades is largely the inertial component of the hub that needs to be rocked backwards and forwards. And if you take that component out, the residual bending on the main shaft is essentially zero, substantially eliminated. So there are three causes of bending that give rise to benefits from the teeter hinge. The first one, and the main one for onshore upwind turbine applications, is that bending loads from aerodynamic asymmetry are substantially eliminated. And this gives rise to a significantly lighter turbine relative to three-bladers. The second is that bending from yaw effects, both inertial and gyroscopic, are greatly reduced. And this enables yaw regulation of a large turbine, which is simply not feasible with three-bladers having fixed hubs. And then the third benefit, looking ahead to floating offshore turbines, is that the bending loads from the offshore platform pitching is greatly reduced. And again, this gives a significantly lighter turbine relative to three-bladers. This diagram illustrates the principle. At the top is a fixed hub rotor with more wind force on one blade than the other, and therefore greater root bending on one blade than the other. And as a result, the main shaft is subject to bending. Exaggerated in this diagram, of course, being a steel shaft, it doesn't deflect so much, but it has significant bending stresses on it. With a teeter hinge, because the whole rotor can rock, you still have more force on one blade than the other, but the root bending is equilibrated between the two blades by the dynamics of teetering. There are several causes of aerodynamic imbalance: turbulence, tower shadow, wind shear, yaw misalignment, and also geometric asymmetries between the blades. And the teeter hinge converts all these causes of imbalance into teeter motion of the whole rotor, not bending of the shaft. In the case of yaw effects, similar things happen because the inertia of the turbine is of the turbine rotor is decoupled from the shaft, and so the effective inertia having to be accelerated around the tower axis is greatly reduced, as if the mass of the rotor is simply a point mass on the shaft axis. And that has similar benefits for gyroscopic effects from yawing, and this enables fast yawing. In the case of floating offshore turbines, platform pitching and yawing and other platform motions are reduced, again because the teeter hinge decouples the rotor inertia. So tower and shaft bending, which are pretty significant loads increments for a floating offshore three-blader, are significantly reduced for the two-bladed teetering turbine. So moving on to the history of teetering two-bladers, the sequence I'm going to run through is the early days of stall-regulated machines, which most of the early two-bladers were. But this is a bad combination because it leads to occasional unstable teetering. In the late 1980s, Windflow's predecessor, the WEG MS3 turbine, was invented in the UK, and that had pitch regulation with pitch teeter coupling, which removes the instability very powerfully, but at the cost of complexity. In the 1990s, Seawind's predecessor, the Gamma 60, was demonstrated in Italy, and that pioneered yaw regulation, which removes this complexity of the pitch system, but without stalling the blades, so there's no teeter instability. And for the last 15 years, Seawind has been scaling up the design, integrating it with a floating platform to leverage these virtues of simplicity and load reduction. So going back to the 1970s through to the 1990s, government programs around the world, United States, Britain, Germany, Sweden, they all went for large two-bladed teetering turbines, transferring the concept from helicopter technology. But there were significant differences between wind turbines and helicopters in terms of ratio of tip speed to wind speed and so on. And stalling as a way of controlling the rotor became inherent and in my view caused problems with most of these designs. The table here just shows the American designs with major companies like Boeing and General Electric, Westinghouse, Lockheed involved, and almost universally they were not very successful. The main exception being the WTS-4 by United Technologies, which was a full span pitch regulated machine, and that ran for 13 years or so. And that had Glid Dolman, an American engineer with a strong helicopter background, and he subsequently got involved in the Gamma 60 machine, which is where the Sea-Wing concept was descended from. But as I say, most had fixed pitch stall regulation, giving unstable teetering. As well as the large turbines pictured, there were also small Danish turbines like the Vestas 40 kilowatt using two-bladed stall regulated teetering, and with very bad results, which I think put the Danes off two-bladed teetering for decades to come. Again, in my view, it comes back to this issue about damping and the fact that if the blades stall, they lose damping, and I'll be explaining that more later. Windflow was the company I set up when I got back to New Zealand based on my experience with the WEG MS3. And that was a major step forward because it produced stable teetering due to pitch regulation and pitch to decoupling. The turbine, as I mentioned, has been built at scale, over 100 turbines, 46 megawatts, still running today in a very windy New Zealand site. More than 1,000 turbine years track record, and it was type certified back in 2010 to Edition 3 Class 1A. When I say it's running today, this is actually from the website showing the instantaneous operation, and this is earlier this morning, New Zealand time. Gale force winds, 90 turbines available out of 91, 92 that they're trying to run at the moment, 90 generating, and they continue to run successfully on a very windy, turbulent site. The Gamma 60 history, that was a joint project between Hamilton Standard, the United Technology, which was where Glid Dolman came in, Aeritalia, Finmeccanica, which was the parent company of Ansaldo, and Silvestro Caruso got involved back in those days in the late 1990s, and Sulsa. And these are the main parameters of it, just showing the maximum teeter angles recorded, which was the main parameter that people were concerned about and should be concerned about in terms of fast yawing. And the greatest excursion was just over 5 degrees, which is getting close to the allowable limit of 5 or 6 degrees. And so one of the main takeaways is that the Sea-Wind design has stretched that out to 11 degrees to give ample headroom for the yaw regulation. This graph shows that yaw regulation does actually work. Both graphs have the same x-axis, the wind speed, and you can see with a yaw angle at top that between about a cut-in wind speed and rated between 4 and 12 meters a second. The turbine is yawed into the wind, yaw angle of 0, and then it achieves regulation at rated power by yawing out of the wind up to 70 degrees or so, as you can see. So to my mind, there's a real synergy of Seawind's key features. Teetering on its own gives you much reduced bending, which leads to a lighter, simpler design, but it also enables fast yawing because of the yaw torques and gyroscopic effects are greatly reduced. And so that enables yaw regulation of the power, which means you can get rid of the pitch mechanism, which again gives you a lighter, simpler design. Another way of looking at this history is that NASA and others largely started with stall regulation, simple and passive system, only one active subsystem, the yawing. But that combination of teetering and stall regulation is not a good combination, has fundamental instability. WEG and Windflow overcame that with pitch regulation, whereas the Gamma 60 and Seawind went another direction, even simpler, with only one active subsystem, being the yaw system. And in my view, this enhances the existing yaw system by combining the simplicity of fixed pitch teetering with the virtues of active regulation. How does the yaw regulation work? Simple terms, the turbine is parked at right angles to the wind, and at startup on the left, the brake is released, the generator motors the turbine up to about 5 RPM before starting to yaw into the wind, so that you've got a good degree of teeter stability, and then it is yawed into the wind, which it continues to be into the wind while the wind speeds are below rated, and then at rated power it yaws out of the wind, yawing anti-clockwise, and then when it comes time to shut down, continues that motion back anti-clockwise into the yaw 90 position to shut down. So in summary, the Seawind has taken a leap forward, next level teetering. And this quote from DNV, who reviewed the technology in 2019, I think is very apt. Our technology is much simpler than the state-of-the-art three-bladed technology. And coming from a teetering turbine background, I can say that it's a logical, well-engineered leap forward. Teetering works to save weight. The Windflow and the Gamma 60 have proved this. The fixed pitch is simpler and previously meant stall reg, which causes instability. Whereas by adopting yaw reg, this is taking full advantage of teetering because the yaw rate can be greatly increased, which enables power control by yaw regulation. And that avoids the capex and opex of the pitch system. And this concept was proved back in the 1990s and has been updated and rigorously calculated using modern computer-aided engineering tools, like bladed. And out of that review in 2019 by DNV, they certified the design of the rotor nacelle assembly to their level D or concept certification or TRL5 equivalent. So yaw regulation fixes the problem of instability of stall reg teetering from the 1980s designs. So in summary, the economic benefit of teetering, less bending, gives a lighter turbine, gives lower cost of energy, all else being equal. And this graph shows nacelle masses of the Seawind designs, starting at 6 megawatt, 12 and 18, alongside comparable mainstream three-bladers from Siemens, Vestas, GE. And for example, the Seawind 12 is about 200 tons lighter than the GE 12 megawatt machine, just in the nacelle mass. And the blue squares represent onshore turbine design, and it is expected that the mass will increase with floating offshore, whereas the Seawind, the turbines have been designed from the start as floating offshore for prototyping, and it is expected that there's some conservatism in the design, which will be able to optimize to reduce the weight going forward. It's an old argument in the wind industry that cost savings follow from weight savings. And considering 200 tons tower top mass, it's hard to avoid that conclusion. It's a fundamental principle which has driven wind turbine development for 40 years. And there's a paper here along those lines. And it's because weight affects the cost of manufacture of the turbine, installation because of the craneage cost, and maintenance, again, because of the craneage costs. Of course, there are some provisos to match the market. You have to be established in volume production, a low-cost supply chain. And so in early days, that full cost advantage will take time to realize. However, it means that you can achieve competitive pricing from the early days because of the weight advantage. Okay, so teetering substantially eliminates bending on the shaft unless you exceed the pre-teeter range, in which case the hub can impact the shaft, causing major bending. So what stops that from happening? And that's going to be the topic of section 2. But I'd like to stop now for questions and discussion. But before I do, let me introduce our guests. Andrew Garrad, Dr. Andrew Garrad, I'm very pleased to welcome you, has had more than 40 years in the wind industry. After 5 years at WEG, he left in 1984 to found and lead Garrad, which became the global leading renewable energy consultancy. So successful and well regarded that in a decade or so ago, Germanischer Lloyd bought in, and now it's fully merged into DNV. Andrew was president of the European Wind Energy Association 2013 to 14 and chair of the Bristol European Green Capital in 2015. In his retirement, he is the Royal Academy of Engineering visiting professor of renewable energy at Bristol University. He retains a strong interest in wind energy technology and politics and still dabbles in mathematical modelling, according to his LinkedIn profile. He is a fellow of the Royal Academy of Engineering and has been honoured by the British government by being made a Commander of the Order of the British Empire, CBE. David Quarton is another fellow of the Royal Academy of Engineering and visiting professor of renewable energy at Bristol University. He started in wind power in 1980 with British Aerospace, which was part of WEG, and stayed with WEG through to 1987. David joined Garrad in 1988 and led the turbine engineering side of their business for most of his time there, including as senior vice president, head of turbine engineering. Dr. Roger Haines is probably the most brilliant engineer I've ever worked with. He was design manager at WEG for 20 years, including 6 years when it was acquired by Neg Micon and then Vestas. In 1986, when I joined WEG, Roger was my first supervisor and mentor. which I hope he has not lived to regret. Over the years, he has been my go-to person when there have been particularly challenging engineering problems to be resolved. He joined Garrad as a turbine engineering consultant in the mid-2000s and continued with them until retiring a few years ago. During this time, he led the consulting team at Garrad, which assisted Windflow obtain its IEC certification. And Steve Gilkes, has Steve joined us yet? Steve is running a bit late, but I'll say a few words about Steve, hoping he will join us soon. He is a visiting professor at Cardiff University's School of Engineering. He's been working in wind power since 1990, when he joined WEG after 12 years with British Aerospace. Since 1994, he has worked for Garrad, Lloyd's Register, and DNV as a senior wind turbine specialist. He has also served as chair of the UK committee, contributing to the development and function of the IEC Renewable Energy Conformity Assessment System. So I'm very pleased and proud to have you all joining this conversation, and now I'd like to throw it open so it is a proper conversation. David.
Hi, Jeff. Can you hear me?
Yes.
Good. Thank you very much for the presentation of section 1. I've got a couple of comments and a question. Firstly, relating to the measurements that you presented for the Gamma 60. Obviously, very valuable database given the development of the sea wind turbines now. The measurements you showed indicated that the turbine was operating at up to 70 degrees of yaw at the cutout wind speed. Do you have any measurements that show, first of all, the maximum and minimum power at that kind of wind and yaw condition? In other words, I'm interested in the power quality, really. And secondly, of course, what the teeter angle was doing by the time you got out to cutout wind speed and 70 degrees of yaw. Do you have those measurements?
The maximum teeter angles I can speak to, because those are recorded on the previous slide as I think the absolute maxima ever recorded, which during normal power regulation was about 4 degrees. As for the power control, power excursions were around 4% maximum.
Sorry, how many percent? How many percent?
4% maximum on power. Of course, you've got the power electronics doing the torque control.
Yeah.
And what needs to be looked at, of course, is the speed fluctuations. But the other aspect is that the control software for the sea wind, certainly, and I imagine the Gamma 60 before, had the electrical torque ramping down.
Okay.
And if the speed excursions got too high, so the speed excursions, I suspect, would have been more than 4%, but between a bit of torque control and speed control, the power excursions were kept to about 4%. I think Sesto put his hand up. Maybe you want to add to that, Sesto?
Yes, I wanted to share what has been required. This was in the first period of operation, with the control still to be optimized. Here is the average values, and these are the plus and minus standard deviation.
Okay. So at 17 meters per second, I guess the yaw angle was what, around about 30 or 40 degrees or something?
70 degrees, Dave.
Yeah.
At 17? So
70.
what's the lecturer saying?
70.
I thought 70 degrees yaw was happening at cutout around 25 meters per second, but anyway, that's a detail. That doesn't matter.
I think the graph was at 17 meters a second, so I assume that they just didn't get enough data in such high winds.
Okay. Because I mean, clearly the power quality and the teeter response of this concept is absolutely key, and those will be the issues that people point to when they first think about the combination of teetering, two-bladers, and yaw control. So it's interesting to see those results.
Okay, Andrew.
Yeah, perhaps not surprisingly, I wanted to look at the same graph, Jeff, because I found that first of all fascinating and secondly very surprising, and I think probably for the same reasons as Dave. So, what I think is missing from that information is a corresponding graph of teeter excursion, and from what you have all said, you've all said that the teeters never hit the stops. Which is just gobsmacking.
That's my understanding with the Gamma 60, and certainly that's the intention with the Seawind designs because of the 11-degree range.
Right, but this has only got 6 degrees here. And the second observation of this, which is also very impressive, is the flatness of the rated power. So when you've got to 1.5 megawatts, you've managed to control it very well. So that's impressive. But then I think what is also missing for me is your predictions of both the teeter angles and the power for these yaw angles, because I frankly find it hard to believe that we can predict how these turbines work at angles of 70 degrees yaw. So I would be surprised if it worked and impressed. But my initial reaction, as I said to you on an earlier email, was I find it hard to believe that you can predict anything beyond a smallish yaw angle reliably, either in terms of power or in teeter angle. So if your aim is to convince the skeptics, I think a couple of other graphs on there, teeter angle with yaw, and also your predictions of these parameters would be very helpful. And so while I've got the floor, there's a couple of other more comments rather than questions. I think when you're getting to the weight comparison, you're being a little bit unfair, because I think you should consider comparing your weights with other concepts. For example, as we go offshore, other people may look at two-bladed turbines, which will be lighter. You can get the effect of a teeter hinge by pitching, and they all now have sophisticated pitch controls, so you can get load control through pitch control, and perhaps that's something you ought to consider, just to be fair. And then you also mentioned no need for a costly PMG. Well, that's a completely separate issue. I don't think that should really be on that graph of comparison. And then finally, I find the whole teetering business absolutely fascinating, and I think people coming to it anew, unlike all of us, and I think this group of people you've got here are the people who spent more time in the whole world thinking about teetering. So they will have been very bored by the first bit of your presentation. But for other people, I think that's going to be very important. What is this teetering? And I found it very helpful to think of it, to think of the two-bladed rotor as a disc, and that disc orientates itself so it has the minimum variation in apparent wind speed as it goes round, and that's what it's doing all the time. So, and if you look at it from the outside, you don't see any teetering. That's also what people look for. So if you saw a disc, you'd just see it sitting there, unless it was doing some maneuver. So I think that spending a bit more time thinking about how to explain the teetering for the uninitiated would be very helpful. That's my comment.
Yes, you're right. There's a good point that actually you don't see the teetering from the side. You see the whole disc of rotation appearing to lean back.
Yes.
because of the combined rotation and teeter motion.
Yeah, but what it's doing, I think the important thing to realize is what it's doing is it's minimizing the variations in the apparent wind as it's going around. That's what it's doing all the time.
Okay, but I stay with the idea of eliminating bending on the main shaft.
Oh, no, that's the effect. No, no, the eliminating the bending is, and you must have equal bending moments at the bottom of each of the blades. Absolutely. No, but the physics of what's actually, the way it steers itself into that position, which you can't see from the outside except in an inclination of the disc, is minimizing the variation in apparent wind. That's obviously not a helpful explanation of it.
that ignores the inertial and centrifugal stiffness terms of the.
Well, they vanish, as you showed later on. The teetering is independent of inertia.
Okay. Silvestro, you want to add something?
Maybe these physical concepts are very, very important to better understand the physical behaviors of the teetering technology. Very, very important. But as you said by email, it is very important to have that confirm of what we think through a detailed numerical analysis. Numerical analysis of the overall system in most body using the most advanced model we are now. These models being the bladed, the fast, and even and the CP lambda, which is a tool developed by Milan Polytechnic, to study the dynamic behavior of the helicopter rotors, which works under any direction of the wind speed, so that under any yaw misalignment. This is fundamental. So we have applied the CP lambda, bladed and fast, and we have applied this tool study at a different level of wind and in onshore, and then in offshore, consider also the weight, the current, how the system responds in a startup, shutdown, normal shutdown, fast emergency shutdown, log variation, and any emergency like the list, the list required by the applicable standard, even the case of loss of grid, the EOG, and so on. So,
okay. I think David's got a question again. Go ahead, Dave.
Just a couple of quick comments in response to Silvestro and also to Andrew. Obviously, I'm a great supporter of bladed, but bladed is just not valid for these kind of yaw angles. If you take bladed or fast or flex, they've never been used and certainly not validated for these kind of conditions. So that's clearly a big challenge when we think about doing some serious proper simulation of the behavior of the turbine. One obvious fact is that blade element momentum theory, which is at the core of all these different wind turbine software codes that are used in the industry today, just is not valid. It needs to be corrected for these high yaw angle flow cases. There are ways of correcting it, but they're not used in the standard configurations of these software. So that's something to be aware of. The second point is, in order to establish the maximum teeter angle that the turbine will ever see, you really need to produce the probability distribution of teeter angles over the lifetime of the machine. So it's not good enough to simulate maybe 50 10-minute simulations. You have to carry out enough simulations in order to build up a description of the probability distribution. This is all written into the IEC standard now, and you may be aware of that, but you have to take a probabilistic approach to establish the maximum value of teeter angle. And I guess that's something that you will do downstream. But then you do have the problem of the validity of the codes in these high yaw angle situations.
Okay, well, that's the interesting point. I mean, I've gained a lot of confidence in bladed through the whole process of the wind flow turbine, and of course our very interesting event of 2005, which we initially modeled with the Excel spreadsheet developed in the 1990s. And I remember Roger coming out to New Zealand and we did a validation of that against bladed, which we were then validating against this event of 2005 where the turbine ran for a while at 80 degrees out of the wind. We seem to get good results in terms of what happened, which was it was very stable as long as the pitch was at fine pitch, which is how the sea wind turbine would operate. But anyway,
Jeff,
I mean, the point's well taken by me. I mean, I've always been a skeptic of computer models. And
what I would suggest, Jeff,
everything's got to be validated by the prototype.
Well, no, what I would suggest is that you could use measurements from the gamma 60 to validate bladed.
I think.
Yeah, that's really what I was saying. That this graph that you've got of the power of the yaw, you could add teeter angle to that, and that would be very helpful. And then try and predict it.
Right. Well, I'm not sure if we've got enough data, good data from the 1990s, but I know young Ben Ralph was working with you on that, Sesto. I don't know how far we got. Can I just get you to comment, Sesto?
Yeah, I wanted to say it before, but then I was listening to Silvestro with all my attention, and then I said, okay. But the point is, yes, we have modeled gamma in bladed, and we have seen that bladed indeed yaws less to keep the constant, to limit the power. But the angles are still that. So it is the turbine, what comes out from the results, experimental results of gamma, it is that the turbine can work more yawed than by the modeling. But the results in terms of teeter are still acceptable, are not changed significantly, let me say. It was not too much data, but the data were there, and that's what we have seen. I'm talking about 7-8 years ago when we did model the gamma, and when we saw this, we did that checks.
Okay.
So Sesto, you were breaking up a little bit, but what I hear you saying is that validation that you did 7 years ago against the gamma 60 data showed that the behavior was being modeled well by bladed. Yeah.
In terms of teeter, yes.
Yeah.
Did you, just saying hi to everybody, but did you show that data to DNV when you had your recent assessment or certification activity with them?
In 2019, Sesto, do you know the answer of that, or Silvestro? Did we show them that data as part of that interaction with DNV?
I don't remember if we had shown also results of gamma? Probably yes, but I am not sure. Silvestro, do you remember?
Yes, maybe yes. But we have to check.
Yeah. Roger, you've been waiting for a while to ask a question. You'll have to unmute yourself.
Work. Okay, I'm unmuted now, I think.
Yes.
Yeah. Just very quick questions. Please explain what is CapEx and OpEx. It's not jargon I'm familiar with. Is there a modest degree of spring in your teeter hinge to keep it central? Because otherwise, I don't see why it doesn't always hit the end stops when it's parked. What holds it away from the end stops when parked?
CapEx and OpEx is capital expenditure and operating expenditure.
Right.
And yes, there is a self-centering aspect of the teeter hinge. It's elastomeric. It's fully elastomeric. So similar to the MS3 and the Winflow arrangement was which had spheroelastic bearings, is a different design patented by Seawind that is going to be used for the Seawind 6 teeter bearings. But it does have a mild self-centering characteristic. I would expect, though, for the storm cases that Silvestro is talking about, the park storm cases, that the rotor would rest against the teeter bumpers in a lot of conditions. This is what we observed with the Winflow machines all the time, and it's because everything's stationary. The loads involved are not significant.
Okay. Is that elastomeric bearing quite a lot softer than the MS3 and Winflow ones? Because they actually were fairly significant in their effect on teeter, if I remember correctly.
Yeah, they'll be of similar stiffness, but I'm not sure I'd say significant. I mean, in the factory, you could lean on the hub and make the hub move by hand. And certainly when the turbine's parked in stormy winds, the wind loads will push the blades around a bit, which will then make it rock a little bit. But as I say, the loads aren't significant,
right,
because the
I'm
turbine's
just
not running.
Suggesting it was not something to be ignored, because I think it shifted the phase in the MS3s. It shifted the phase of maximum teeter by 20 or 30 degrees.
Oh no, that was the pitch teeter coupling, Steve. The pitch teeter coupling is much more significant in terms of shifting the system away from resonance and therefore changing the phase angle.
Okay, yes.
It's an aerodynamic stiffness term.
Yes. Yeah, I remember that. Yeah.
Yes, I certainly don't remember the spheroelastic bearings entering significantly into the calculation. No.
Okay, yes. Sorry, that's my lack of recollection.
Can I just ask one more question, Jeff? The Gamma 60. It's just the obvious question you're going to be asked. Gamma 60. Why didn't that go ahead then, and what is different now?
Well, I think you've got to cast your mind back to 1990, late 1990s. Oil prices were going down. I remember a economist cover story at the end of the century when people said oil is going to be less than $10 a barrel. There was very little interest in renewable energy globally. Of course, the Danes were carrying on and Texas was starting to pick up, but those four large players in the Gamma 60 project decided for various reasons that they weren't going to go ahead.
Yeah, so just commercial rather than technical.
Yeah.
The owner, of the company which made Gamma 60 in the West, and the winner was the Finmeccanica. And so that in a perspective, there was no market for wind turbine. So they decided to stop any implementation and industrialization, to close the production line. Many years after this event, Mr. Gliderdoman, which is the helicopter engineer who understood the advance of materials moving from the helicopter to wind turbine, along with me, made up a company, Gamma Venture. So we together, through the Gamma Venture, move ahead, having bought the rights of the Gamma 16 from Finmeccanica. So from this point on, Gliderdoman and me continue to work on the industrialization of these technologies, and later me along with our company like Seawind and so on, and the colleagues like Zestro and so on.
Okay, before I go ahead with section 2, I see David, you've got your hand up again. Did you want to ask something? And Andrew. So David first.
Oh.
It was a mistake, really, Jeff. But just while I'm on the line, just a quick one. There have been examples of stall-regulated T2 turbines that have worked very well. I'm thinking in particular of the Carter turbine, which I think was a very successful machine. So there are examples of where it can work. It all depends on the aerodynamics of the blade, of course.
Okay, I remain skeptical, but how can you get the aerodynamics working properly, given that's the purpose of stall regulation? Oh, I remember the Carter machine didn't really regulate, did it? Its power curve kept on increasing with wind speed.
Yeah, it had a pretty lousy power curve, but it was stable in Teeter.
Well, yes, so it didn't power regulate. But if you power regulate properly, you're aiming to get the integral across the rotor of the in-plane forces leveling off, so that there's no change with wind speed, and therefore no change with angle of attack. And my simple thinking is the same must be true of the out of plane stepwise moments, that it's effectively DL d alpha has to be 0 if you stall regulate properly.
I think all I'm saying, Jeff, is perhaps you don't say that stall regulation in combination with Teeter is fundamentally unstable. It doesn't need to be.
Oh, I beg to differ. I mean, I vividly remember getting back to New Zealand in 1990, and a local power company had put up a Windane or Vestas 40 kilowatt machine on the Port Hills, and every time it got a good southerly come through, so you had above rated winds and a bit of turbulence coming over the top of the Port Hills, the thing ended up on the ground. And I tried to explain it to them and predicted it. But anyway, it to me it has to follow from this argument. Anyway,
I just point to the Carter turbine, but anyway, it's not a central issue. Let's leave it.
Well, but if the power regulation isn't horizontal, if it's it continuing to increase with wind speed as the Carter power curve did, then that's how they maintain.
Jeff, you're well known for being obsessive.
Pardon?
You're well known for being obsessive. You can moderate your language slightly, and David will be satisfied. I have one pedantic note to make, that you keep saying the pitch flap coupling or delta 3 hinge increases stability. It doesn't. It increases stiffness. It decrease the Teeter excursions, but it doesn't have any effect on stability. I think you need to be careful about saying that. I think it's wrong. I suggest we don't talk about that now either.
It shifts you away. It shifts you away from resonance, though, right?
Yeah, it gives you stiffness. Yes, it gives you stiffness, But resonance and stability, people often make that mistake. Instability and resonance are not the same thing. What the delta 3 hinge does is add stiffness to reduce excursions. It will change natural frequency, but it doesn't affect stability.
Well, I think the fact that I'm now working for Seawind, which doesn't have pitch teeter coupling and relies on aerodynamic damping for its stability, is testament to the fact that I agree with you, Andrew, and I've learned that lesson. I used to be a great advocate for pitch teeter coupling.
If this is a sales pitch to innocent people, you need to be a bit careful that you don't make the statements you make are factually correct. And it honestly doesn't matter that in terms of this Seawind, but you shouldn't say it.
Okay. I can't remember where I did, but anyway, okay. Anyway, look, I'll carry on with my presentation if that's okay. Before leaving section 1, I'd like to present a few more slides that we have produced following the meeting you have been watching. These go into some more detail on a couple of the questions raised. The conversation at the end of section 1 raised two important related questions. Are there fundamental problems, limitations with modelling wind turbine behaviour at high yaw misalignment angles? And has Seawind validated its numerical models against Gamma 60 data? And was this data given to DNV for the review in 2019? On the first of these questions, further discussions between the experts have taken place. An important point was made about models which are all based on stream tube theory. Highly yawed operation will mainly occur in above rated winds. Stream tube theory is mainly concerned with determining the axial retardation, i.e. the amount by which the wind speed at the rotor disc is reduced. This has a maximum value of 33% of the free stream wind speed, a maximum which occurs at below rated wind speeds. Axial retardation is significantly reduced to less than 10% in above rated winds. Therefore, variations between models and reality will be fractions of 10%, i.e. second order effects. This is not to say they should be ignored. In terms of our plans for model validation, Seawind has already adopted the advice of DNV's bladed experts to use the dynamic inflow option for wake modelling as being the most accurate for high yaw misalignment. Furthermore, we intend to explore the inflow distortions caused by high yaw misalignment with wind tunnel testing. We've obtained a proposal from Professor Carlo Bottasso at the Wind Energy Institute at the Technical University of Munich to conduct wind tunnel testing of a highly yawed model turbine to validate CP lambda and bladed at model scale. This will focus on the degree to which distortions of the induced velocity at the rotor disc will occur and change the angle of attack of the blade sections, affecting performance and loads. We expect to carry out this work and other tests during the construction of the Seawind prototype at TU Munich. Regarding Gamma 60 data and the 2019 review, Seawind can confirm that Gamma 60 monitor data, including teeter angles during emergency shutdown, were provided to DNV in 2019. This information was part of a large set of documents provided to DNV for its review, which resulted in them certifying the Seawind 6 megawatt and 12 megawatt rotor nacelle assemblies at the concept certification level, DNV level D. DNV did not ask for validation studies based on the Gamma 60 data. Seawind has been separately progressing model development and validation against Gamma 60 data. These models included the original Hamilton Standard model from the 1990s and Seawind's more recent bladed 4.5 model. While a full validation of the 25-year-old Gamma 60 data was not possible, these models both agreed with the data reasonably well. The main discrepancies, which may have been due to an instrumentation issue with the Gamma 60 prototype, were with respect to modelled versus monitored yaw misalignment values, but the teeter angle values agreed well. The following graphs of monitored gamma 60 data show very stable teeter behavior when operating in high winds at high yaw misalignment angles and during a shutdown due to an extreme gust and wind shift. The two graphs on the left show wind speed and direction, and the bottom left graph you can see halfway along at about 60 seconds there's a significant wind shift of 50 to 60 or 70 degrees. The top graph shows wind speed generally being above 15 meters a second, mainly around 20, but with a gust to 30, 35 meters a second. That's 60 or 70 knots during the wind shift. On the right, you've got the rotor speed and teeter angle graphs. And you can see that there's an overspeed during the gust and wind shift event, followed by a shutdown. Teeter angle stays quite stable during this whole period, increasing to 4 or 5 degrees during the overspeed and wind shift event, and remaining quite stable during the shutdown. The DNV report on the C16 and 12 noted the gamma 60 demonstration of yaw regulation as providing limited field history. This is their term for when things are not fully proven, but not completely unproven. They awarded concept certification status, DNV level D, to the C16 and 12 rotor nacelle assemblies, and set out a plan for type certification for which the next major step would be construction of a prototype of the C16. CWIN agrees that this is the next logical step, which will enable formal validation as required for type certification of the latest numerical model, Bladed 4.12, against C16 prototype data. So I trust this has answered the issues raised, and we can now move on to section 2.